Hello and welcome to the presentation of our paper titled Resilient Periodic Observer-Based Control for Wide Area Oscillation Damping Against Time Synchronization Attacks. This video is created for ISGT 2022 conference. Here are all the authors and collaborators of this work. I am Saghar, the first author. I've been a PhD student at Concordia University, Montreal, Canada, at the Department of Information and Systems Engineering since 2018. This research is done in collaboration with Dr. Amini, who recently finished his postdoctoral fellowship at Concordia, Dr. Ghafouri, assistant professor at Concordia, Dr. U, research scientist at Hydro-Quebec Research Institute, Dr. Mohammadi, and Dr. Debabi, who are both professors at Concordia University. Let's start with the introduction. It is crucial that the generators of a power grid all operate at the same frequency. If a generator deviates from the synchronous speed, low-frequency oscillations are produced that, if not dealt with through controllers, might lead to grid instability and blackouts. In the modern power grid, wide-area oscillation damping controllers have been possible thanks to time-synchronized measurements and advanced communication networks. However, alongside the many benefits, this application is prone to cyber-physical threats. Since the time synchronicity of measurements is imperative to the wide-area controller's function, an adversary might attack the time synchronization aspect of the measurements used in this application to degrade its performance. The type of time synchronization attack that is modeled in this study is called the first-order time synchronization attack, which can be described as a step function, and its impact is measurement loss. The proposed controller in this study is a sample data observer-based controller resilient against this type of attack. We use sample data control protocol in this study to be suited for digital implementation and closer to the real-world deployment of PMUs. Our approach provides a priori resilience toward the attack and can be applied during the parameter design stage. Now let's go over the problem statements. In this slide, we can see the linearized model of the two-area four-machine contour system. Here we can see the block diagram of the system and the proposed periodic observer-based controller. Using the PMUs and the observer, we can measure or estimate all the system's states. Here we see the equation that models the observer. The control protocol in this study is feedback control, which is shown by U equals Kx. Our goal is to design the observer gain and the controller gain. The attacker manipulates the time reference of the observer sampler by adding a constant error to it. If this error is significant enough, the measurement will be dropped. The attacker has active and inactive intervals. During the active interval, the controller input will be 0 due to the measurement drop. The attacker's energy is limited, hence the active and inactive intervals. But our approach does not impose any assumptions regarding the pattern or distribution of the attack, which is compatible to the unpredictable nature of the adversary. Here we can see the closed-loop equation of equations for the duration of inactive and active attacks, respectively. We designed the observer gain L via LQR method so that it is Hurwitz stable. Before designing the controller gain, we decide the values of the sampling period, the stabilization rates, and the resiliency level. Then by solving some linear matrix inequality conditions, the control gain is designed. In this slide, we can see these LMIs and the relation between them and the controller gain K. More details of these matrices can be found in the paper. In the end, our controller is designed with resiliency of omega, and omega of 0.1 means the system stability is guaranteed if attack intervals do not occupy more than 10% of the total operating time. Now let's see the simulation and its results. We implemented our controller on the contour system in MATLAB Simulink. You can see the topology of this grid on this slide. In this slide, we see the effectiveness of our proposed controller in maintaining the system's stability while a 10% attack is launched. The active attack intervals in these two scenarios are uniform, meaning the duration of all active intervals are similar to each other. One scenario is fault-free and the other one is in presence of a three-phase fault. The last scenario shows the effectiveness of our controller in the face of a non-uniform attack, while a fault has also happened. All these results show that while the average attack time is less than the resilience level, our controller guarantees the stability of the system. Thank you very much.